Welcome back, linear algebra fans. This is going to be a video lesson about an intro to determinants. And you might be thinking, haven't we already talked about determinants before? Why are we doing an intro to determinants now when we've already seen them? And the answer is we've only seen them for 2 by 2 matrices. And we need an intro to determinants in a more general sense. What about n by n matrices? So that's what this lesson is going to be about. Also, if you're following along with the textbook for this course, this is the beginning of a new chapter. I think at this point in the course, we're actually going to start skipping around. We're going to skip around a bit throughout the book and cover some topics. But yeah, this is the beginning of chapter 3 in that book. All right, let's go ahead and get started. So an intro to determinants, in particular, trying to focus on cases that are larger than 2 by 2, but I will do a quick review of what we've seen so far. We need to kind of remember the 2 by 2 case because it might help us with the more general case. So we've said that if A is a 2 by 2 matrix, A, B, C, D, if it has an inverse, remember, not every square matrix is invertible. If it has an inverse, it is A inverse equals, we have a formula, right? You could say 1 over AD minus BC times D negative B negative C A. And we say that the determinant of A is that denominator, AD minus BC, which turns out to be a pretty important number. We can tell from the formula for an inverse that if the determinant is 0, this is going to be undefined because we would be dividing by 0. So in fact, A is invertible if and only if the determinant of A is non-zero. Now, we can kind of tell that for the 2 by 2 case. And in fact, this sentence is going to be true for the general n by n case as well. But we just haven't figured out how to compute a determinant for larger cases. That's what we need to talk about. We had some notation about determinants. We write the determinant of A as, you could say determinant and then just write the matrix. That's one way you could write it. Or another way is, remember we had this notation with straight bars instead of the square brackets that we usually put around a matrix? Just straight bars. They kind of look like absolute value bars, almost. Anyway, those are determinant bars. That's how we should think of them. And we're going to use those quite a bit in this lesson. So if you haven't used that notation before, hopefully you'll get used to it by the end of this lesson. Oh, and another thing that I'll say is we wrote this up above with letters like A, B, C, D. But we could also write the matrix as A11, A12, A21, A22. And in that case, the determinant of A is A11, A22 minus A12, A21. Same thing we wrote above, just labeled differently. That might turn out to be helpful later because, you know, as we get to like the 3 by 3 case or 4 by 4 case, we're probably not going to be calling the entries A, B, C, D. We're probably not going to use consecutive letters of the alphabet. We'll probably just switch to this kind of notation. You know what else? I said we were going to look at larger cases. Let's have a brief discussion of a smaller case. What about 1 by 1 matrices? Now, I want to remind you that this concept of a matrix being invertible You know what? I'm not going to write this. Let's just talk for a second, okay? I'm putting my pen down. What does it mean for a matrix to be invertible? Besides this determinant thing, what does it mean to be invertible? A matrix times its inverse equals the identity matrix. That's important, right? A times A inverse equals the identity matrix. So, and also the other way around. A inverse times A equals the identity matrix. All right, so we could, if we had two things and we thought one of them was the inverse of the other, we could verify by multiplying them, matrix multiplication, and see if they multiply out to the identity matrix. Okay. And it's only a concept that we talk about for square matrices. Now, 1 by 1 is technically a square matrix. We don't talk about them very much in this course because they're not very interesting. But let's talk about it briefly. What if A is this 1 by 1 matrix? It just contains this one entry, lowercase a. In this case, we define the determinant of A. I'm going to give you a formula. Are you ready for this formula? It equals A. That's it. Because what else could it be? There's not really any other entries that could be involved. And I want to say, notice that the matrix A is invertible if and only if the determinant of A is non-zero. Let's do an example. I wasn't planning on doing an example of a 1 by 1 case. Let's just do one. Let's suppose that we have the matrix A equals 5. Then the determinant of A equals 5, which is non-zero. So A is invertible. Okay. What do you think the inverse is? I haven't given you a formula for the inverse of a 1 by 1 matrix, but what do you think it is? Well, keeping in mind that A times A inverse has to equal the identity matrix. Side note, the 1 by 1 identity matrix is this. Remember, an identity matrix is supposed to be a square matrix that has ones along the main diagonal and zeros everywhere else? Well, this has a 1 along the main diagonal. So anyway, this has to be 1/5. Then A times A inverse equals I. I'll just put a little check mark next to it. That does work. So 1 by 1 matrices, very simple, not much to say about those. You're probably not going to really get a question that asks you about 1 by 1 cases, but I thought we should spend a minute on it. And I did think that it was worth verifying this idea that it is invertible if and only if the determinant is non-zero. The determinant just happens to be very simple in this case. All right, so most 1 by 1 matrices are invertible. What other case is there? How about we just go to n by n? N by n matrices where n is greater than or equal to 2. And, you know, we're assuming n is an integer. I said n is greater than or equal to 2, so everything we say here is still going to apply to the 2 by 2 case that we already know how to do. But it's also going to work for larger cases. So for n by n matrix A, we let Aij denote, this is an uppercase A, so it's not just going to be an entry of the matrix. This is something new for us. We usually use uppercase letters for matrices, right? Capital A is a matrix. Capital Aij is also a matrix. It's going to denote the submatrix formed by deleting the ith row and jth column of A. So this is a tool that we need for what we're going to do. And I'll give you an example. I think an example will help a lot with this. Let's say we're given a 3 by 3 matrix A. Let me just give you a chance to catch up here. So we're going to make a new matrix by deleting a row and a column. So in my little example here, I wrote a 3 by 3 matrix, and I've said A23. Well, A23, we're going to delete a row and column. I know which row and which column. Here's what I'm going to do. I'm going to write all of the matrix A, and then we're going to cross out the part that we're deleting. So we're not done. We're not done until we actually cross some things out. Let's get another color pen here. So the instructions say that we are supposed to delete the ith row and jth column of A. So what is the ith? Well, I is 2. So what is the second row? Second row is getting deleted. Okay. And we need to delete the third column. Let's do that as well. And then we write, what are we left with? After deleting that row and column, I still have 1, 3, -2, 3. So we get a smaller matrix because we deleted 1 row and 1 column. This is a tool that we need. And it's worth pointing out that if you delete 1 row and 1 column from a square matrix, you always get a square matrix. The 3 by 3 became a 2 by 2. So it's still square. Also, just to point something out to you, what entry was at the 2, 3 location? The entry that was at the 2, 3 location, like you go down 2 and over 3, it was this. I mean, I don't know if you can see that I'm circling this, but it was the one here. It was the intersection of the deletion that took place, the 7. So what you could do if you wanted to find A23 is go to the 2, 3 entry and say, all right, everything in that row needs to be gone, everything in that column needs to be gone. And then what am I left with? So we won't always write this out. Sometimes we'll just do this in our head and just write the result. So we need to talk about the determinant. And how does the determinant use these submatrices that are written in this way? We define the determinant. I'm going to warn you that this is defined in a little bit of a weird way, but we're going to see it written in a couple of different ways, and we're going to see examples. We define the determinant of A to be the sum of all n terms of the form plus or minus A1J determinant A1J with plus or minus signs alternating. So that is the definition as a sentence. It actually seems like if we had a 3 by 3 matrix A, the submatrices are 2 by 2, and we know how to do the determinant of a 2 by 2. So maybe it's good. This idea of taking a large matrix and deleting rows and columns gets us smaller square matrices until you get down to the 2 by 2 size, and we know a formula for the determinant of that. All right, I told you I was going to write this in a couple of different ways. So that's it. That's the definition as a sentence. Let's also write it in symbols. So in symbols, the determinant of A could be written as A11 determinant A11 minus A12 determinant A12 plus, because we're alternating pluses and minuses, A13 determinant A13. How big is this matrix? We don't know, because we're talking about an n by n case, so we don't know how far we have to go. But we add and subtract alternating until we get to the last term. Is the last term going to have a plus in front of it or a minus in front of it? What do you think if we're alternating? Plus, minus, plus, minus, plus, minus. Well, this was kind of a trick question. The last term gets a plus or a minus depending on the size of n. It depends if n was even or odd. So I'm just going to not put a symbol there, but it's a plus or a minus. A1n determinant A1n. This is a 1 here. All right. So the determinant of a large matrix, presuming that A is large, is defined as this alternating, I don't know if I want to use the word sum. It's kind of an alternating, yeah, you could call it a sum. It's a sum, plus, minus, plus, minus, plus, minus. It's a sum of determinants of smaller matrices. So if this was 3 by 3, these smaller matrices are 2 by 2, and we could use the formula for the determinant of a 2 by 2. Or if we really wanted to, we could technically say this method, this definition is supposed to work for n greater than or equal to 2. So even a 2 by 2 matrix, you could use this and break it apart into 1 by 1 matrices. And we know how to find the determinant of a 1 by 1 matrix. I'll show you another way to write this as a more compact formula. What's a good way to write a long sum in a more compact formula? Sigma notation. Write big Greek letter sigma. Let's say this goes from j equals 1 to n, because it's an n by n matrix. And I want to say, well, if you look at what I wrote above, I basically want to say A1j determinant 1j, like this right here. I want to say this, A1j determinant A1j. But how do I deal with the plus or minus that alternates? Well, if you've taken Calculus 2, you remember that when you write a series and you need alternating pluses and minuses, you can do that by doing -1 raised to a power. And this works if you do 1 plus j. And now I can write A1j determinant A1j. So that is the definition of the determinant as a formula, assuming that A is a square n by n matrix. So which of these do you prefer? Do you like the sentence? Do you like the way I wrote it out in symbols? Do you like the way I wrote it as a formula? Let's do a 3 by 3 example, and I'm going to do this first one because I think examples will help this make sense. So let's compute the determinant. You know what? When we compute the determinant, we might, in particular, we might be interested to know, is it 0 or not? But for now, this is just simply going to say compute the determinant. and it's going to be a number. The determinant is always just a number. It could be positive, it could be negative, it could be 0, it could be a fraction, a decimal. We don't know. An integer. It's going to be a real number. Okay, I'll do this one. We're going to use this new definition. This is 3 by 3. I think what I'm going to do, you know how we wrote this up here in symbols? I'm going to do this, but it's only 3 by 3, so I only need 3 terms. So I'm going to say that the determinant of A is equal to A11 determinant A11 minus A12 determinant A12 plus A13 determinant A13. That's the whole thing. You end there because it only goes up to 3. So let's figure out what each of these pieces are. What is the lowercase a11? That's the entry in the 1, 1 position. So that's 1 times the determinant of. What is capital A11? That is the submatrix that you would get by deleting row 1 and column 1. Can you just do that in your head? Delete row 1 and column 1. And I'm left with 0, 1, 2, 1. That's my first term. There's going to be 3 terms altogether. Minus A12. A12 is the 2. And then determinant of capital A12, the submatrix formed by deleting row 1 and column 2. Or you could go to the 1, 2 entry that we actually just used that too, and say delete this column and this row. What are we left with? We kind of cross out things in the shape of a letter T, and we look at what's left. We have the 3, the 1, the 4, and the 1. 3, 1, 4, 1. And then plus A13. Oh, A13 is -1. So plus a negative number. And then the determinant of what's left if you remove row 1, column 3, we're left with 3, 0, 4, 2. All right. We still have work to do. Can we finish it on this page? I think we can. So each of these are 2 by 2 determinants, so let's just use the formula for a 2 by 2 determinant. Wasn't that formula like AD minus BC? So we can just kind of do that quickly. This times this minus this times this. So let's say, I'll write it out. That's that one. That's that one, AD minus BC for that one. There's a -1, and then 3 times 2 minus 0 times 4. I wrote it all out. And this is going to equal a number. We have 1 times -2 minus 2 times -1 minus 1 times 6. This is -2 plus 2 minus 6. Final answer, -6. So that's about how much work it takes to do a determinant of a 3 by 3 matrix. We actually had to do a bunch of 2 by 2 determinants within the problem. So I'm going to give you one of these to try. We're going to move this page and I'll give you a problem. Okay. Same type of problem, same size. Compute the determinant. Of A equals 1, 0, 3, 4, -1, 2, 0, -2, 1. So I'd like you to pause the video and try this. All right, let's do this like we did last time. Maybe, as we do more of these, I think I'm going to be writing less and less each time. So I'm going to use the straight vertical bars notation this time. I think that that's a little bit more compact. So we get 1 times the determinant of this submatrix minus 0 times the determinant of this submatrix plus 3 times the determinant of this submatrix. And if you compare with the previous problem, in the previous problem, I wrote out the word det, det for determinants. So let's just compare. This line right here, I wrote determinant of this 2x2 matrix, determinant of this 2x2, determinant of this 2x2. Just use the vertical bars and it's more compact. You don't have to write det in front of it. Vertical bars already tell us we're taking the determinant of what's inside. Okay? So I like the vertical bar notation. Hey, you know what? Look at that 0. Isn't that great? That 0 means we can just cross this out, because whatever that 2x2 determinant is doesn't matter, because it's going to get multiplied by 0. So we can just skip that part. So we have 1 times, what do we get here? -1 minus -2 times 2. So minus -4 is plus 4. And then what do we get over here? 4 times -2 is -8 minus, 0. Just be careful with arithmetic. You don't want to make a mistake at this point. I mean, everybody makes mistakes now and then, but try to catch them if you do. So this is 1 times 3. So this is 3 plus 3 times -8. Final answer, 3 minus 24 is -21. There you go. And there's only one correct answer for these. A matrix has a unique determinant. So we've just seen 2 examples of 3x3 determinants. I want to show you one that's 4x4. And I'll do the 4x4 case. And it's going to say find determinant A given. By the way, you might be wondering, are there going to be any shortcuts? Yeah, there's going to be a shortcut soon. It's still going to take a bunch of work, but anyway, let's do a 4x4 case. There's no shortcut that's going to magically take all the work away, but there's some shortcuts that'll make it a little bit easier for some problems. But I am going to show you, based on what we've said so far, that I can find a determinant of a 4x4 matrix. And I think if we do this 4x4 case, then you'll believe me that this method also works for 5x5, 6x6. I mean, what we gave earlier was a definition of the determinant, so it has to work. It's not like it's a theorem that we need to prove. It's a definition. So by definition, the determinant is found in this way. So what do we do here? We go across the top row, right? We take the 2 times a submatrix plus 1 times a submatrix. Oh, I said plus, I meant minus, because we're alternating plus, minus, plus, minus. Here's what I'll do. I'll write it instead of saying it. 2 times determinant of this submatrix. What do we get when we delete row 1, column 1? We're left with this, which is 3x3. Okay, minus 1 times determinant of a submatrix. When you delete row 1 and column 2, you get 0, 0, 2, 7, 3, 5, 0, 0, -3. Plus, we're supposed to alternate plus, minus, plus. But what's this entry? This entry is a 0. So 0 times some kind of submatrix I'm just going to put a 0 here as a placeholder. I'm not even going to write the submatrix. I don't even want to waste my time figuring out what the submatrix is because it's getting multiplied by 0 anyway. So let's just move on to the fourth and final term. We alternated plus, minus, 4 times this submatrix. So that sort of missing third submatrix that I didn't bother writing because it had a 0 in front of it, I think it was still good that I wrote plus 0 because it helped me make sure that I was alternating plus, minus to make sure I had a minus in front of this 4. Okay. Can we figure out what this is? Well, okay, it looks like we have 3 problems there. We have to figure out the determinants of this 3 by 3 matrix, this one and this one. So let's just do these as 3 separate little problems now. I have the vertical bars, which mean determinant of, and I'm just going to break this up into the three sub-problems, I guess. So what's this determinant? We'll figure out all 3, and then we'll put them all together. -1 times this determinant of this submatrix minus 0 plus 2 times the determinant of this submatrix. It's starting to feel like it's really nice when you're doing a problem and it has a bunch of zeros in it. Doesn't that seem nice? Zeros mean we get to just skip a part. So I get -1 times -9 plus 2 times 0 minus 3. I get 9 minus 6. I get 3. All right, so that part of the problem is 3. Let's move on to the next part of the problem, which is another 3 by 3 determinant. 0, 0. Oh, I'm looking forward to this one because it says zeros in it. Look at that. You go across the top row, right? You take the first entry, the 1, 1 entry, and then the 1, 2 entry. So look at this. 0 times a submatrix minus 0 times a submatrix plus, I'm only writing them to make sure that I'm alternating signs so that I could figure out if this needed a plus or a minus in front of it. All right, 2 times the determinant of this submatrix. Even this has zeros in it. This is 2 times 0 minus 0. This is 0. So the determinant of that 3 by 3 matrix is 0. We've got one more 3 by 3 determinant to do. And then after we do that, we have to piece this all together to find the final answer for the 4 by 4 problem. Oh, again, we've got some zeros. Let's say 0 times something, which I'm not even going to bother writing, minus -1. We'll do that just to be careful. Minus -1. Submatrix 7, 3, 0, 0. And then what? Plus 0 times something. So minus -1 is +1. And then what is the determinant there? 7 times 0 minus 3 times 0? It's just 0. You know what? I was going to do this on another page, but we only have one more line to go, and we can finish this problem. We're not done. One line to go. Let's just remember what we're doing. We're finding the determinant of this 4 by 4 matrix. We said that it equals this. We broke it up into these 3 sub-problems, and we found each of them. We found a 3, a 0, and a 0. I want to put the 3, 0, 0 into this and figure out the final answer. So the determinant of A was the 4 by 4 matrix, is going to be 2 times 3 minus 1 times 0 minus 4 times 0. Final answer is 6. So it's okay if you have a big problem to break it up into smaller problems like this. I mean, that's kind of the whole point of the definition of the determinant. By definition, it takes a problem and breaks it up into smaller problems. You see, we started with a 4 by 4 matrix, and in our work, we've got 3 by 3 submatrices, and we have 2 by 2 submatrices. Final answer is 6. Now, I said something about a shortcut. I also said something about how it seems really nice when there's a lot of zeros in a matrix. So this is theorem 1 for this chapter. Theorem 1, I don't think this theorem has a name, or it could. Maybe in some textbooks this might have a name. All right, I'll write this out first, and then we'll talk about it. The determinant of an n by n matrix A can be computed by finding the sum of the n terms plus or minus a ij determinant a ij. That's a little different from what we said in the definition. Across any one row or column of A where signs alternate according to hold on, let's move this up. The signs alternate according to this picture. It's a square matrix, but we're not assuming how big it is. It could go on, it could be 10 by 10 or whatever. We alternate according to this. Maybe you think of this as like a checkerboard pattern that keeps going. Plus, minus, plus, minus, plus, minus. Do you see what's happening on the diagonal, though? Diagonal's all pluses. Well, anyway, this theorem here, you know what? Let's put something in parentheses here. Specifically, because you might say, why are we drawing a diagram? That doesn't seem very precise. So specifically, the sign in front of aij, determinant aij, is, doesn't it seem like we should be able to do -1 raised to some kind of power to give us either a +1 or a -1? Yeah, -1 to the I plus j. All right, I'm going to put that in parentheses. That part in parentheses is just saying what the diagram says. So, what is this theorem really saying? I underlined the word any to put emphasis on that. That's my own emphasis. What we've been doing so far when we find determinants is we've been basically going across the top row and using the entries in the top row and, forming submatrices by deleting rows and columns. This says you could actually do that kind of process across any one row or column. So the idea is that this could be a shortcut because you might look at a problem and you might see that row 1 is really messy, but row 2 looks easier to work with. So you get to choose which row or column you do the work with. A couple of things before I show you an example. First of all, we call determinant of aij the I comma j cofactor. This is just some terminology. And the overall strategy is cofactor expansion across a particular row or column. So in that sentence there, this is me just pointing out some terminology. I probably don't use those terms very often. I'm mostly saying them in case you see them in the book or in case you see them somewhere else. If somebody says, oh, I want to compute the determinant, and I'm going to do this by cofactor expansion across row 2. Now you know what that means. Cofactor expansion across row 2 means you do what we've been doing, except you're using row 2 instead of row 1. All right, let's do an example of how this theorem saves us time. And I'm going to do an example. Well, actually, I think this is going to be the best example I could show you is let's redo that 4x4 matrix, but we're going to redo it in a more efficient way. So find determinant of A given that same 4x4 case, 2, 1, 0, 4. So a few minutes ago, we did this by the definition of the determinant, and there's nothing wrong with that. But we're going to see if we can save ourselves a little bit of time. All right, same matrix as earlier. When we did this by definition of the determinant, you saw how much work it took. It probably took about half a page. We had to figure out a bunch of we broke it up and we had to find 3 3x3 determinants. So let's discuss this, and we're going to solve it faster by using the theorem, but I want to explain what's the difference. So previously, we used Aij, determinant Aij, in other words, the ij cofactors, across row 1. Why did we use row 1? Because that's what the definition told us to do. The definition of the determinant has a bunch of 1s in it. And we did determinant A11 minus 1 determinant A12 plus 0 determinant A13. That one was nice because it was a 0. Minus 4 determinant A14. Actually, a few of these turned out to be zeros, but we didn't know that until we did it. So, you know, in particular, we had, you know, this, and this. These were like 3 3x3 determinants that we had to figure out, and it took a while. So now, according to Theorem 1, we can sum across a different row or column. When it says row or column, it means horizontal or vertical. You're not allowed to use the diagonal, okay? So which row or column do you think looks the most convenient? There's one in particular that I think is the best. Any of them would work. You want to use like column 4, and then you've got like 4 times a submatrix, you know, minus 2. You could do that, but no, I think the one that looks the best is column 3. Column 3 is easy because it has the most zeros. If we do that cofactor expansion across column 3, starting up here and working our way down, as long as you do the whole column, that's okay. Let's be careful about pluses and minuses. You could refer to this little diagram up here and say, all right, well, if we're in that spot, we start with a plus. I mean, it's a 0, so it doesn't matter. But it does matter by the time we get to the non-zero entry, right? So, okay, 0 times the determinant of A13 minus 0 times the determinant of A23 plus, this is why it was important that we got the pluses or minuses off on the right start, 3 determinant of A33 minus 0 determinant A43. And you see what's happening here? earlier when we did the problem, we were able to basically cross one of them out and we had to do 3 problems. But now we can cross out 3 of them and we only really have to do 1 problem. That's what makes this a nice shortcut. You find the row or column that has the most zeros, do cofactor expansion across that row or column. You get to cancel as much as possible. Here, let's go to another page and let's finish this. We're going to make it even easier. Let's make this even better. So this equals, this is the only part of the problem that we actually have to do. So let's just write 3 times, what is this submatrix? So look at the entry at location 3, 3, and imagine deleting that row and that column and see what you're left with. You're left with 2, 1, 4, 0, negative 1, 2, 0, 1, negative 3. So we have to figure out this determinant, right? 3 times this determinant. Are you thinking about, like, 2 times a submatrix, 1 times a submatrix, 4 times a submatrix? No, don't do that. Don't do that, right? Let's use this. Let's use this column. This one has the most zeros. This is going to be the most convenient. So let's sum across column 1 for this problem. So I think I could go back and circle it here as well. So we used column 3 because it had the most zeros. And then in this problem within the problem, column 1 has the most zeros. So let's use that. So we need the 3 out front. Don't forget that 3. But then we're going to have 2 times the determinant of this. And then what? Minus 0 times something, minus 0. We can write it, but it's going to get crossed out anyway. So you don't have to write the parts that I'm crossing out, but I'm just showing you that this is why it works out so nicely. Zero in front, cross it out, cross it out. So do you see what's going on here is we're trying to do a 4x4 determinant. By, clever use of this theorem, instead of all the work we did earlier, now we only had to do 1 3x3 determinant. And in that 1 3x3 determinant, we only have to do 1 2x2 determinant. It worked out that way for this problem. Maybe this problem was set up conveniently, or maybe we were just being really clever with paying attention to zeros. Okay, so the 3 out front times 2 times this 2x2 determinant. This 2x2 by, negative 1 times negative 3 is 3, minus 2 times 1 is 2. So 3 times 2 times 3 times 3 minus 2 equals, we know what the answer is because we did this earlier. We got the same answer that we got earlier. But the point that I'm trying to make is that this was a whole lot easier. So that's the determinant of this 4x4 matrix. It's 6. And just real quick comparison. This is how we did it the first time. I can't even fit it all on the screen, but this is how we did it according to the definition of the determinant. Technically, there's nothing wrong with that. It's completely correct. We got the answer of 6. You could do it that way every time if you want. But theorem 1 told us use any row or column that you want. The most convenient row or columns are going to be the ones with lots of zeros. So, really, this was all the work right here. It's a lot shorter, and we got the same correct answer of 6. Cool. So, let me show you. There is a theorem 2. But I feel like right now, with that example that we just did, I feel like you could do a lot of determinant problems now. I could give you 2x2, 3x3, 4x4. Maybe even a 5 by 5 if it has like a bunch of zeros in it. Maybe a 5 by 5 problem wouldn't be so bad. Just hopefully it has some zeros in it to make the problem quicker. If it doesn't have zeros in it, well, then you're stuck. You got to do it the hard way. Okay, theorem 2. If A is a triangular matrix, remember what that is? A triangular matrix represents a triangular system. Then the determinant of A is the product of the entries on the main diagonal. This is another shortcut. Let's do an example. I mean, we could do a proof or we could do an example, but I think I would rather do an example. So I'm going to show you, let's say we want to find this, and it has the vertical bars, so you know that it's asking you to find the determinant of this matrix. I'll do this for us, though. So, I mean, the theorem says just, you know, here, we're going to do this both ways. Answer by theorem 2, you just do 2 times 5 times 3. You get 30. Boom, we're done. But why does that work? Let's talk about why that works. What if I did cofactor expansion across the first column? The first column has the most zeros. If it's a triangular matrix, then the first column is going to be a very convenient one to work with. So I'm going to do cofactor expansion down the first column. So 2 times determinant of this submatrix minus, do we need to do the rest? Minus 0 plus 0. All right. This is 2 times, look what it winds up being. What's the determinant of this 2 by 2 matrix? 5 times 3 minus 0 times 0. Do you see that this is just 2 times 5 times 3? So that's the reason why this theorem is true, is if you did cofactor expansion down the first column, that it would work out this way. You could do cofactor expansion across a different row or column. You'd also get 30. But this is a nice shortcut. You don't even have to do the cofactor expansion if it's in triangular form. Now, you might be wondering, this kind of raises a natural question. And that is, if you had a 3 by 3 matrix and it was not in triangular form, would it be okay to do row reduction to get it into triangular form and then apply theorem 2 to get the determinant very quickly? And is that a valid strategy or not? Does it get you the correct answer or not? And I'm not going to answer that question yet. I'd like you to think about it. You could actually try it and see for yourself whether or not it works. But we're going to talk about that in the next lesson. It's still something that you could start thinking about. Is that a property? Is that a shortcut? For now, I do have another cool thing to show you. So far in this lesson, we learned the definition of the determinant for the n by n case. We did 3 by 3 problems, we did a 4 by 4 problem, and then we had theorem 1, which made the problems even faster because we can use any row or column of our choice, and we've done a 4 by 4 problem. And now theorem 2 is useful for triangular matrices. If you're lucky enough to get a triangular matrix, you just apply theorem 2, and that's maybe the fastest kind of determinant problem there is. The one more thing for this section is that there is also another trick for 3 by 3 determinants. And this is also going to be a shortcut specifically for the 3 by 3 case. Now, you know how the 2 by 2 case has a specific shortcut? You know, because the definition that we gave earlier today, that applies for n greater than or equal to 2. So technically, cofactor expansion could work in the 2 by 2 case. But when it's a 2 by 2 case, we usually use this. 2 by 2 determinant and a 2 by 2 inverse. I guess really I should just be pointing at this. For finding the determinant of a 2 by 2, we usually just use this. AD minus BC, right? Okay, so it turns out that there is also a trick or shortcut specifically for 3 by 3 cases. Now you might say, is it going to be some big formula like AD minus BC, but bigger? Not really. It's not really going to be a formula. It's going to be more of a strategy. So let's label all these entries like this. I don't know why I labeled them like this. I could have called them A11, A12, whatever, but we did this. So I'm going to show you a 3-step process, okay? 3-step process. This might seem weird to you. Some students like this method and some students don't like this. It's not a method that you're required to use, but let's see if you like this method or not. Step 1, write a second copy of the first 2 columns to the right of the matrix. This is a 3-step process. I'm going to do each step as we say it. So we wrote it as a sentence, and now let's actually do it. So here is our matrix. GHI. Close the matrix. And this step is telling us write a second copy of the first 2 columns to the right of the matrix. That seems weird, but let's just do what it says and see where are we headed with this. That's what it says to do. I wrote second copy of the first 2 columns to the right of the matrix. All right, step 2. If step 1 seemed weird to you, step 2 might seem weird also. Multiply entries on the 6 diagonals. Okay, I need to draw a big picture here. Leave yourself some room to label things on this next one. First of all, I'm going to write what we just had, but I'm going to leave a little bit of space above and below it. A, B, C, D. I guess I don't need to recite the alphabet while I'm doing this. A, B goes here, D, E, we're just copying. All right, what 6 diagonals am I talking about? Well, in what we've written here, there's the main diagonal. You know about that. But the main diagonal, A, E, I, there's now also some new diagonals. There's B, F, G, and C, D, H. That's a couple more. And we could also go the other way and do like H, F, A. So let's write some of this. The main diagonal from the original matrix goes A, E, I to get us AEI. The next diagonal that we made, B, F, G, if you multiply those all out, you get BFG. And C, D, H, multiply those out, what do you get? CDH. Of course, in an actual problem, These would be specific numbers. What are the other three diagonals? It's going to be, what if you went in this direction? G, E, C. With me so far, you see how there's going to be two more? Let me move this page. Do you see what the other two are going to be? HFA looks like the next one. HFA. We're going to do something with all of these products. IDB. IDB. All right. That's step 2. We're done with step 2. I said this was going to be a 3-step process. All right. Step 3. This has to get us the determinant because we're on the last step. Add the downward diagonal products and subtract the upward diagonal products. So that the determinant of A equals AEI plus BFG plus CDH. Those ones are added. And then subtract the other ones, GEC, HFA, IDB. Wow. So I guess technically it is a formula. Maybe earlier I said it wasn't going to be a formula. Technically it does look like it's a formula, but I usually don't think of it as a formula. I think of it more as a strategy, as I will show you in an example here. Okay. So I wouldn't worry about memorizing this formula. It's not about memorizing the formula. If anything, the thing that you would want to memorize is probably step 2. It's like, what do you do? Like, what's the idea? And then the idea that the downward ones get added and the upward ones get subtracted. So I wouldn't worry about like memorizing the step 3 formula. All right, example of using this trick for 3x3 determinants. And I'm going to start with one that we did earlier, and I'm going to do this one. And then I'll ask you to try one after this, to try out this method and see how you like it. So I think we did this earlier using the definition of the determinant. I want to show you this with this new method. So I'm going to write the matrix, leave myself some space for all the stuff that's going to go around it. 4, 2, 1. I'm going to copy row 1, 1, 3, 4. I'm sorry, column 1, and column 2, 2, 0, 2. And let's get started doing these diagonals. Multiply these out. What's 1 times 0 times 1? 0. Multiply these out. What's 2 times 1 times 4? 8. Multiply these. Negative 1 times 3 times 2, negative 6. Let's go the other way. 4 times 0 times negative 1. There's a 0 in there, so the product is 0. 2 times 1 times 1 is 2. 1 times 3 times 2 is 6. So we get those pretty quickly. And by using this method, the determinant is supposed to be, you take the downward ones and you add them. 0 plus 8. Well, one of them has a negative in front of it, so I mean, we're adding negative 6. All right, now subtract the other ones. Minus 0, minus 2, minus 6. What does this get us? Zeros. 8 minus 2 is 6, minus 6, minus 6. We get negative 6. And we got that pretty quickly. So it is a shortcut. It's kind of a weird method. I think it seems different from everything else we do in linear algebra. So I don't know if you like this method or not, but you can use this if you want. Just keep in mind that this is only for 3x3 cases. All right, let me give you one to try. And I'd like you to try this method. In the future, I'm not going to specifically force you to use this method, but for right now, I would like you to try it out to see that you understand it and see if you like it, and that way you can decide if you want to use it in the future. 2, 2, 3, negative 1, 1, 3, 2, negative 2, 0. Okay, I'd like you to find the determinant using this method. Okay, so did you pause the video and try it? I'm going to write this out. Leave ourselves some room. So 2, 2, 3, negative 1, 1, 3, 2. See how finding determinants is really just a whole bunch of multiplication. Multiply a bunch of numbers, add and subtract a bunch of numbers. Well, you have to know which things to multiply and which things to add. I guess that's the trick to math, isn't it? Knowing which things to multiply and add. This is 0. This looks like 4 times 3 is 12. And this looks like positive 2 times 3 is 6. Let's do these ones. This looks like 6. This looks like negative 4 times 3, so negative 12. And this looks like 0. Okay, determinant of A equals the downward ones get added. Let's not even write, I'm going to skip writing the zeros, like 0 plus 12. Let's just say 12 plus 6 minus 6, and then minus negative 12. I'll write it that way. Okay, whatever number this equals. And then there's a minus 0 that I didn't write. So what do we get? Oh, 6 minus 6. Get rid of that. 6 minus 6 is gone. 12 minus negative 12 equals 24. So that's the determinant of this matrix. So what do you think about this method? It's a little weird. We're not going to see anything else like this in this course. It's just a trick for 3x3 determinants. I mean, also, by the way, we didn't prove that this works, but there's a simple way to prove that this works. All you would have to do to prove that this method works is find the determinant. Here, I gotta move up. Find the determinant of this general 3x3 matrix using the definition of the determinant and show that it equals this formula. And if you do that, then you've proved that this method works. I'm just skipping that for the sake of time. So I think what I would suggest is I might sometimes use this method and sometimes not, depending on what the matrix looks like. So if the matrix it's very situational, right? How about this? I'm gonna flash some pages in front of you for a moment. If the matrix is diagonal, I would use theorem 2. 2 times 5 times 3, it doesn't really get much faster than that. So if it's a triangular matrix, I should say. If it's a triangular matrix, I would use this method. What if it's not triangular? If it has a bunch of zeros in it, I would use theorem 1. And I would find the row or column that has the most zeros in it, and I would probably just do cofactor expansion, especially if there's a row or a column that has 2 zeros in it, or if there's a row or a column that has 3 zeros in it. In a 3x3 matrix, if you have a row or a column with 3 zeros in it, do you see that that's going to work out really simple? If you had a problem that did not have that many zeros, that's when I might use this method, because it's still pretty quick. So you decide, it's up to you. We've seen a bunch of different methods for finding determinants now. Okay, so that lesson was called Intro to Determinants, and we learned how to compute determinants for the general n by n case. I think you could solve a lot of problems now. You could do 3 by 3, 4 by 4, etc. Um, the next lesson I'm going to tell you is called Properties of Determinants. And one of the main things that we need to discuss in that section is something that I kind of hinted at earlier, is if you have a square matrix, is it okay to do row reduction and then find the determinant? Does that get you the same determinant? Because, when you row reduce, you get a bunch of zeros in a matrix, and it seems like, wow, now it's like triangular form. I could just get the determinant really quickly. Is that okay? And we actually need to discuss that in some more detail, whether or not that gets you the correct determinant, because it turns out that each type of row reduction step that we do, we need to check what effect does it have on the determinant. If we interchange rows, if we add a non-zero multiple of a row to another row, if we multiply a row by a non-zero constant, how do each of those affect the determinant? And then we'll be able to get an overall answer to, is it okay to row reduce? So anyway, I'm getting ahead of myself. We'll talk about that next time. So thanks for watching, and I'll see you soon. Bye.